I'm going to be talking a lot about generative design and the role of the designer as computers become more powerful and start to be our allies in helping us to create our designs. The role of the designer is changing dramatically in the fact that we're going to be now focusing on asking the right questions instead of focusing on how do we draw the thing that we're designing. And this changes the thought process and even the pedagogy of how we train and teach designers to take advantage and lead the next generation. I also expect that out of this, people will learn how to rethink the way that they approach design and even the tools that they're using to help them go through their creative process.
So let's start. What are we going to talk about? Failure. Why do we want to talk about failure? Why do we want to set ourselves up for failure? It seems counterintuitive, right? Isn't design about finding the right solution? Well, I would argue that the process of design is really about finding failures before you get to what is the right solution, right? There's no formula for design. There's no equation that you can put in and say, here is the right answer. It's a very complex problem, has multiple objectives. You're trying to solve for many things at the same time, right? You're trying to make people happier, trying to consume less energy. So it's a very complex problem, and we have to iterate through design to find our best solution. So what we're going to talk about is this nature of design and how we can use machines to help us design better and help us to go through more iterations. So let's start with a scenario. Let's say that you're this poor gentleman here, and it's your first day on the job, and you're a product designer, and they told you, you need to draw this structure. Right? You see this web-like structure with these thousands of little elements? They say, we need you to draw this, so you start drawing it. And as you can imagine, that would take a very, very long time to point and click your way through something as complex as that. And then you're very happy and you bring it to your boss. By the end of the week, you've finished it, and he said, oh, wait a minute. We made a change. You need to redraw it. You're like, oh, man. I just spent a week drawing this thing. Now I'm going to spend another week drawing it. So obviously, drawing something directly is what we call explicit design. You know, you're taking the idea in your head and you're drawing it out on the screen. This thing was not generated by someone drawing it. This thing was generated by the computer. And we're going to see more and more of what we call generative design, where the computer helps us to draw and helps us to solve problems. And what's interesting about this is that it ends up giving us solutions that we may not have thought of on our own. You can see these three objects here. Can anyone guess what those objects are? They look kind of weird, right? They look a little alien. These are actually structures that connect the flap of a wing to the wing structure itself. It's a hinge. Now, it's probably not a hinge that you or I would design. It's not really something that we've seen before. This was a product of generative design of one of our research groups called The Living, which is actually an architecture firm that we acquired a couple of years ago. And they used generative design and developed their own algorithms to go through iterations. And you see this graph below here, right? This little zigzaggy thing. Each of the lines in that graph represent a solution, a thread. And all those vertical lines that you see are different objectives. I want to minimize weight. I want to maximize strength. I want to maximize stiffness. I want to minimize the amount of energy I use. Again, every design problem has multiple objectives. And those are those objectives shown in a graph form, and then each of these solutions, it shows how well it performs against each of those objectives. Now, the blue and the purple ones are highlighted because they perform the best out of these sample sets, but you can see the number of threads behind there of how many different iterations were tried before we found the right ones. This looks like what design will be in the future. At least I argue that this looks like what design will be in the future. So you're like, well, what about sketching, man? I love to sketch. How many people in here like to sketch stuff? Yeah? We have some designers in the room. Look, sketching doesn't go away. We love sketching because it's easy. It's low overhead, right? You know, some of us have migrated now to designing on a digital sketch pad. This is using a sketchbook. But regardless if you're sketching digitally or on paper, traditionally, it's easy to take an idea in your head and to put it out on paper. At least for most people. For some of us who are more challenged in drawing, it might be harder. But we love this because it's very fast and we can iterate quickly, right? We can draw something, we can erase it, we can try it again. It's fast. It's low overhead. It's easy to go through this process. And I don't think this is something that's going away, but I think the nature of what we sketch will change. Again, here, we're sketching the idea of a car. We have an idea for the car in our head, and we draw it out on paper. And I think that will change. All right, so humans are their best when faced with a blank page. Machines don't know what to do with a blank page. You go to a blank page, it gives you a blank stare. Creative people can see this as opportunity to start something new, right? To express a new idea. Now, what's changing, though, with generative design is that we have a certain idea of what things should look like or how they should perform or how they should behave. And I think that we need to suspend our belief about what things should look like. That when we start sketching now, we're going to be sketching the problem that we're trying to solve. We're going to be sketching the connections between the elements of the problem that we're trying to solve. Less so about drawing the thing that we think is the right idea, because quite honestly, our first idea is not usually the right idea. So in exploring this concept, I realized that it kind of changes the way that design is taught. I went to architecture school for undergraduate and did engineering in graduate school. And you're taught how to come up with ideas and how to draw them and how to test them and evaluate them. And I was thinking, in this new paradigm, it's really more about understanding the problem, asking the right questions, and then teaching the machine how to draw many, many iterations for you. So earlier this year, I taught a course called Multidisciplinary Design and Optimization at Stanford. And it was interesting because there were students from a broad set of backgrounds. We had product designers, we had civil engineers, we had mechanical engineers, we had architects, all in the same class, and they're all working together as teams. So that alone was kind of interesting. But I realized that I should have named this class Setting Up for Failure. Because that's really what we're doing. We're trying to set up a problem and teach a machine how to find a million bad ideas before it found a good one. Now the problem is most students wouldn't sign up for a class that's called failure, right? It's not exactly inspirational. Yeah, Dr. Brandt, I want to go try to find out how to fail really fast. But this is the kind of ambiguity that we need to embrace. And what was interesting in that course, where we had the engineers and then the designers like the architects and the product designers, the designers were very open to the ambiguity, open to the idea that they didn't know the answer. However, the engineers, once we got into instructing the computer of how to come up with the designs, excelled. So we really leveraged the value of both disciplines and both educations. All right? And I'll show you kind of a quick view of some of the results of this class. So they started sketching, right? Moleskin, blank piece of paper, just like you normally would, except what you can see is they're not sketching the thing. In this case, we're designing a building that would minimize the amount of energy it consumed. They weren't drawing buildings. They were drawing the relationships of the components of the buildings. How do things connect? What impacts the amount of energy consumption? And then we program the computer. But we program the computer with this technology we call Dynamo, which is a visual programming language. So each one of these nodes is a set of relationships, and you're connecting the relationships. So we're really teaching the machine now how to go through thousands of iterations, thousands of design options. So it took a long time to program and put the relationships together. But once we did, the number of output exponentiated, right? Traditionally, maybe you could draw 3, 5, maybe 10 options. It was very hard, though, to draw 1,000 options in time for your design review or in time for your product deadline. So this is what's changing. This is the paradigm that's shifting, focusing on the problem definition. Now, let's look at kind of the traditional process of design, explicit design, and this is what I call pre-cloud human transactional, which is really a fancy way of saying the way that we traditionally do things. Let's say that we're designing a building or an airplane, and you have multiple disciplines that have to design that, right? You have the architect, you have the structural engineer, you have the mechanical engineer, you have the electrician, you have multiple disciplines. And so let's say that I'm the architect, and I design the form, And then I send the file to the structural engineer who designs the structure. And then the structural engineer sends it to the electrician who designs the circuits, so on and so forth. So it's incremental, it's a serial linear process. And it's quite easy to do, so we can start from day one and be productive, but it's really kind of a linear progression of how many iterations we can go through. Now let's look at this something else we call cloud-enabled human collaboration. So this is something we started learning a lot as a startup before our company was acquired by Autodesk, where we had created a cloud collaboration software for three-dimensional design. So you could design your building or your plane or your car in the cloud simultaneously with all of your team. So your structural engineers might be in London, right? Your mechanical designers might be in Shanghai. You have distributed teams, and so now you're all designing simultaneously in the cloud. And what it enables you to do is go through many, many more iterations. You don't have to wait for someone to finish their work before you start your work. You're all together, unified by cloud technology. So as you can see, the rate of progression is much steeper, but it's still linear. And it's still humans driving the process. So what's this third one? Machine augmented collaboration. When we work with machines to help us design, you can see the number of iterations that we go through starts off almost exponential. We can go through thousands or millions of permutations, and then it kind of goes through this logarithmic curve as it starts to coalesce on a solution, and then we find the solution. So the theory here is that the more iterations we go through, the better design that we can create, right? So how do we teach the machines to do this? This is a cute little movie, a short film that a friend of ours at Autodesk put together. He's a huge Star Wars fan, and he said, well, what if R2-D2 fell in love? And in this case, R2-D2 fell in love with a mailbox. So you can see this blue mailbox with a little pink bow. R2-D2 is walking through the park, found the mailbox, they fell in love, and he courted her, and they ended up getting married. And I'm not going to tell you how it ends, but there's a nasty battle with lightsabers in the end. The point I wanted to bring out here is that R2 wanted a portrait of himself and his new lover. So he taught his friend, this robotic arm, how to draw. So this robotic arm is actually, it's a force feedback machine, which means that you can grab its hand and you can literally teach it how to draw. And that's how we did it. Again, explicitly teaching it how to draw this design, how to draw this form, grabbing its hand and guiding it through the process. Now, I don't know why he put a bikini on the mailbox. Evidently, they didn't want an R-rated image of themselves. But this was really fun, good idea, but this isn't what we talk about when we say teaching a machine how to design something. There's a precedent for how to teach machines to learn. Who's used Google image search lately? I'm surprised not everyone raised their hand. Anyone who's ever done a presentation uses a lot of Google image search. Pretty much every image in here came from that. And obviously, we love to search for things like cats. And if you've used Google image search in the last year and a half, 2 years, you've noticed that its ability to identify the cat that you're looking for has improved dramatically. So, in fact, let's say I'm looking for cats, but I really like this frowny, our favorite friend, Grumpy Cat. Some people say that this is what I look like normally, and I'm like, no, I'm just thinking really hard, okay? So I'm not grumpy, I'm just contemplating. And I think that's he's misunderstood, he's just contemplating life. So let's say I like Grumpy Cat. I click on Grumpy Cat, and you see these suggestions over here. It's found these suggestions through machine learning to identify other images that look similar to this Grumpy Cat. And the thing is, we didn't explicitly teach this machine how to find other images. We didn't say, this is what cat looks like, or this is what a grumpy cat looks like. It's using machine learning algorithms and simulated neural nets to find its own way to learn about cat. And what's kind of interesting here, and the engineers at Google released a paper about 2 years ago saying that it actually performs better than they thought it would, because the machine is generating its own code. It's modifying its own performance over time. And it actually is performing better than they thought, and the only way they can tell you exactly how it identified any specific image, they have to reverse engineer the code that the machine generated. So think about that for a second. The machine is generating its own code that it then uses to evaluate an image. And if it does really well, then it modifies that code again. So the original programmers don't know what new code is going to produce necessarily. It's kind of scary, but it's kind of exciting if we use it properly, right? And this is progressing very, very quickly. Google acquired a company called DeepMind, based out of London, and they're teaching machines how to play video games. And there's a really great video you can watch where it learns how to play an Atari game, and it can outperform any human, and it does so after a few hours of learning. And they don't teach it how to play the game, they just say maximize the score, and you figure out how to play the game. Now, a video game, especially an Atari game, is quite simple, but these are being adapted to more complex systems. So in our world, at Autodesk and as designers, we like to think about designing three-dimensional things and building three-dimensional things. And so we now have design tools that are in the cloud. So this product called Fusion 360, which by the way is free for all entrepreneurs if you want to try it out, is a cloud-based 3D modeling tool. And it could do lots of cool things, but the point I want to bring up here is that because it's in the cloud, we have all of this data about the 3D designs. And this is really the first time that we're amassing a large amount of three-dimensional data in the cloud. And now we can start to think, well, how do we do image search for 3D? Right? You can find a face or you can find a cat, but how do I find a gear? How do I find a chair that's similar to this one? So what we're building is three-dimensional image search in a project we call Design Graph. What you're seeing here, it looks like a Petri dish, right? Like a laboratory, and you look under a microscope, and these are little bacteria. These are actually the search results for searching on those the 3D models you just saw. And each one of these little squiggly lines are a grouping of similar objects. All right, so you can think about now, what if you could potentially have an autocomplete, just like you type in a Google search and it completes it for you. What if you could potentially do that with 3D models? So if we zoom in on one of those little groupings, one of those search results, this is what you'll find. In this case, it's a bunch of nuts that have been aggregated. Now, the machine doesn't know what a nut is. It doesn't know what function it provides. It doesn't know what it's made out of. All it knew was what shape it was. So it recognized that all of these things have one hole in them, and they had this kind of approximate shape. And so it logically grouped them together. It did pretty well. Did the same thing for gears. It realized that this thing has one hole in it, and it's got a really rough, jaggedy edge. It grouped them again just based on shape. We didn't tell it what a gear was. Now what's interesting, once you can start finding geometries just based on the shape, now you can start figuring out what geometries are connected to other geometries. So if you're going to have a gear, you're probably going to have a shaft that you put the gear on. And you're probably going to have a nut to attach the gear to that shaft. And you're probably going to have another gear that gear attaches to make it turn, and maybe a motor, and so on and so forth. You see where I'm going? That you can now start to figure out, if I'm designing a gear, it can start suggesting, hey, would you like to have a belt or a gear or a cog to connect to that design that you already have? Which is pretty cool. Like, who wants to spend all their time? How many times have humans redesigned the same thing over and over and over again? And I argue that most of us as designers are probably not seeking out to design the new gear. We just want it to work, right? We want the computer to do that work for us. Our minds are best applied in other areas. So this is great to think about in autocomplete for design. The thing is, though, there's not a lot of imagination. If I'm just reusing existing designs that humans have already done, where's the creativity? Right? I would just end up with an assemblage of things that look more or less like what we already have. It is a picture of a bug that naturally grew its own gears. Us humans, we thought, we invented this amazing mechanical contraption. Well, nature figured it out a few million years ago. It's on this little thing called a leaf hopper. Issus coleopatris. So the reason that these gears evolved is because these little leaf hoppers are tiny. They're all over the world, very proliferate. And when they're jumping from one leaf or one piece of grass to the other, they have to be very precise because these things jump a very long distance. So you can imagine it has two little legs. If one leg jumps harder than the other, it's going to go in the wrong direction. It's going to miss its target. So it needs to make sure that it fires both legs exactly at the same time. The problem is when this is small, when it's a larva, when it's a baby, it doesn't have enough neurons in its brain to fire them at the same time. It's not developed enough. The motor control isn't there. So naturally, it evolved these gears to make sure that both legs fire simultaneously. It's pretty cool, right? What's even more interesting is that over time, these gears go away. As it becomes an adult and its brain advances, it doesn't need the gears anymore. So it's almost four-dimensional in the sense that it only has them as a baby when it needs it, and over time, it evolves away. It's fascinating. So what do we learn from that? What do we learn from natural evolution? Well, we're doing something where we're taking what we call genetic algorithms. So think of the gene, in this case, is the DNA for the design. And we chop them up, and we mix them up with a bunch of other chromosomes and recompile them and come up with a new design. That's really kind of how natural evolution works, right? Random mutations. That's how we find innovative solutions. That's how nature finds innovative solutions. So what you're seeing here is a very much slowed down video of a design that is being grown. And these two surfaces on either side are the constraints. So this is to grow a bracket, and we need to hold a certain amount of force at a certain distance, and we want to minimize how much this bracket weighs. Those are the objective criteria for this design. And so it grows a design, it evaluates its performance. Structurally, how does it perform? How much does it weigh? It ranks it, and it does it again. And the cool thing is, it does this about 3 times a second. Right? It's computing in the cloud. It's using almost infinite computing resources to go through all these iterations and figure out which one works best, which in this case was this thing, or that thing, which is probably not something that you or I would have come up with. What this structure actually does, the yellow thing here, is the fuselage of a lander that's being sent to the moon next year by a startup that's in Silicon Valley called Moon Express. All right? So because this thing's going into space, you want it to weigh as little as possible because it's very expensive to put payload into orbit. And this gray thing that you see on the side is the thruster, right? So as it's landing, this is where the rocket, the thrust is coming out. So it has to hold this thruster at a certain distance. Now the point here isn't about the details of how to design a bracket for a thruster on a lunar lander. The point is, it came up with this really crazy solution that was better than anything that our human designers had done, and it doesn't look like anything a human designer would do. In fact, if you were asked to draw that, you'd probably say, no way, man, that'd take me a week, just like the poor guy in the first slide. The problem is, and think about this for a second, if this is simulated natural evolution, it's just trying random things and see what works, which is fine because it's in a computer, so it can do that very fast. But it still has to go through thousands and thousands or even millions of iterations before it finds a good solution. Genetic algorithms are a good way to find bad solutions or bad ideas very quickly. And you have to do enough of them to come up with a good idea. So it's really not very efficient, right? Evolution took hundreds of millions of years to yield humans. And humans have brains, and we're able to develop technology which accelerates evolution in a way. So how can we accelerate what we want to do? How can we accelerate this process and not just randomly search every possible permutation? Well, I would argue that this is where human-machine collaboration comes into full view. Right? We hear about robots taking our jobs, or how do we work with the robots, or the Terminators are going to kill us all, and eventually they probably will, but that's another story. But we need to collaborate with the machines in order to get the best of both worlds, right? We want the intuition that human designers have that's kind of impalpable, something we can't yet teach a machine. But we also want the efficiency that the machines provide, the ability to go through that many iterations, the ability to look at things in resolution that we can't comprehend. So it's not an either or, it's very much a both and. So let's look at a case study very quickly of how we can put these things together. So this is a company called Lightning Motorcycle. They build electric motorcycles that go really, really fast. So if you think of electric vehicles as being slow and boring, this thing goes 218 miles an hour. It's winning a lot of races, and it's all battery powered. So as you can imagine, a racing motorcycle, you want it to be as lightweight, as stiff, as strong as possible. So we looked at the case of this little thing called a swing arm, which is quite important. It's the thing that is circled here. It holds the rear wheel onto the structure of the motorcycle. So the suspension attaches to it, the rear wheel attaches to it, the chain goes through there, and it hinges on the chassis. So we said, okay, we want to redesign this, we want to make it lighter, and we want to maximize the human-machine interface. So this is how it's traditionally made. It's made out of, they take one big block of aluminum, and they machine away all the material that they don't want, which is incredibly wasteful, right? You start with a big block, you take away all the material, so you end up using like 10% of the material you started with. And if anyone knows anything about aluminum, it's incredibly energy intensive to produce that block of aluminum. Incredibly energy intensive. So we just wasted a lot of energy by machining away the stuff that we don't want. Plus it's quite heavy, as you can imagine, right? It's structural, it performs its role, but it's quite heavy. We can do better. So the first iteration we said, okay, what are the constraints that we can't change, right? And those are things like where it attaches to the structure, where the rear wheel is attached to the axle, where the suspension attaches. These are fixed things, we can't change that. So let's lock those down. Those are constraints. And then we do an analysis to figure out what the loading conditions are. And if you guys aren't familiar with finite element analysis, this is basically a heat map of the stress. So red areas have a lot of stress, blue areas have very little stress, and green is somewhere in between. So you can see here there's a high area of stress concentration. Over here in this area, this blue area, there's not much going on. All right, so we did the analysis. Now the first iteration was me taking that analysis and trying to optimize it on my own, right? I was using a computer to draw it, but I was explicitly drawing it. I was pointing and clicking and creating the design. This is what we came up with, which is a hybrid 3D printed and machined structure. So the white part, that mesh design, is 3D printed. This is machined aluminum out of a block of aluminum, so we minimize the amount of material that we wasted. And it was much lighter and met the requirements of the original structure, but we're like, you know what, we can do better than that. Let's get machines involved. So we used a technology we call Dreamcatcher to shave away, carve out all the material that we didn't need. So you remember the heat map, that structural analysis with the red and the green and the blue? This basically took away all of the blue areas, because it's structure, it's material that we don't need. And as you look at it, this is probably, again, not something that you or I would have come up with as the most logical solution. It looks pretty alien, to be honest. In fact, we went through, again, many iterations of this to figure out which one worked the best. But in this case, it was guided. It was guided by a human who understood and had intuition about what this thing needs to do and what it, how it should perform. And so this is an interface, and this is a part of this research, is how do you get a human designer to interact with millions of design options? It's not a trivial thing. You can't just look through every single one of them and say that one works, that one doesn't. So we can rank them, and we're researching how to build interfaces to help the human curate and choose which design. So now you can choose, I like this design and this design, breed these two and give me a new generation. Treat them as parents and create new generations of these kinds of designs. So this is pretty fascinating research. Now the end result, the one that we ended up printing, is this one on the top. And you see it's almost perfectly symmetrical except for this hole. Can anyone guess why there's a hole in one side and not the other? Does anyone ride motorcycles here? Come on, I know you guys all have scooters. There's a chain, right? The chain has to drive the wheel. So there's a hole where the chain goes through. Now these other things are pretty similar. They look kind of the same. Those are bones. Those are the pelvises of a dog and of a cat. Our CEO likes to go to a bone store, and Berkeley, California is probably the only place in the world that has a bone store. And he likes to go and browse around there, and we had been working on this project. He went in and he saw these bones. He's like, oh my God, these look very similar, at least conceptually, to this design that we optimized. And it's true, right? We are going through basically artificial evolution. So it's logical that the things that come out of this look very organic. And fortunately, it didn't take hundreds of millions of years to optimize that design, like it did for the pelvises of the mammals. Now, the only way that we can make this stuff, this organic-looking, weird stuff, efficiently really is by 3D printing it, all right? Additive manufacturing is a way to go forward with very organic designs. And fortunately for us, 3D printing is getting very real in the sense that we're not just printing the concept or the prototype, we're printing the actual thing. You know, we're using all kinds of different materials now to be able to print with metals, titanium, Inconel, carbon fiber, right? So just even at my desk, this is at Autodesk in San Francisco, my desk, this machine sits there, it's about this big. It's really beautiful, it's designed really well. It prints in carbon fiber, and it prints in Kevlar, which is the bulletproof vest material, very strong. So with this little thing that sits on my desk, I can print real stuff. You know, if I want to go rock climbing, this is a little carabiner that I drew up very quickly. This was not generatively designed, this was human designed. But I can actually hang off of this thing. I can hang on the rope from a rock wall. It is structural, and it prints in about 45 minutes. And I can print different ones. Every one can be different. Doesn't cost me any more. This stuff is getting real. This is a technology, a company that we acquired a couple of years ago called Within Labs, and we've recently released Within Medical to design medical implants for humans. What you're seeing here is a hip cup, right? So you have a ball and socket joint in your hip. This is the socket. Now the reason that structure looks like this, it's like the trabecular structure in your bones, right? Your bone, if you cut it, has this really rough cellular structure. This helps to promote bones to grow around the implant. So one of the problems with implants today, first of all, they come in a few sizes. They have like small, medium, and large. And I would bet that of all of us in the room, none of us perfectly fit into a small, medium, or large hip cup. So you can print exactly the size and the structure that you need, and you can print it to promote adhesion to your own bone structure, right? There's really no other way you can make this thing. This is a fun project we're working on with Joris Larman, who's a designer out of the Netherlands. He taught robots how to 3D print stuff. So he was using some of our software to make the designs and then started creating the machine code that would instruct the robot how to print this. It's basically a welder on a robot that's precisely controlled. And you can see he can print coming out of the wall, growing out of the floor, coming out of the ceiling, and can print any kind of form, really crazy shapes. So what could you do with something like this? Well, the project we're working on is to actually print a bridge over a canal in Amsterdam. Yeah, this is something we're planning to do in 2017 to actually print this bridge. And the way we're going to do it is we're going to put a couple of robots there. We're going to give them a bunch of steel, and they're going to start printing it on their own. And as they print some of the structure, they'll move out on the structure further, and then they'll print more of the structure, and they'll move out on the structure. So they're going to print from both sides and come in and connect it without humans. It's pretty cool, right? Now you look at the structure here. Doesn't it look a lot like the trees, the branching structure here, which is not unintentional? It's beautiful. And the idea that this can be really performance art as it's being created. Now the thing is that we have to learn how to accept is that this stuff does not look like the way we think it should look like. This is not exactly what we think a bridge should look like. Now, for designers in the room, maybe we're more accepting of that. Maybe we're intrigued by this. I mean, I think it's beautiful personally. But what about the rest of the public? I mean, will people trust a bridge that looks like that? So this is about suspending your belief. Suspending your belief about what you think should look like, about that preconceived notion that the first sketch is the right sketch, right? And we're creative people, so we need to help the public to understand what is about to come. And I truly believe that this is the kind of design that's going to come. So to help advance these kinds of projects, this kind of technology, Autodesk announced a $100 million investment fund for 3D printing startups. So my day job is evaluating companies who have great ideas around additive manufacturing, and we get lots of them. Most of them aren't good ideas, but again, just like natural evolution, out of every few hundred, you get a couple of good ones. And really, the goal here is to promote additive manufacturing as a whole, generative design. So this includes the machines, the 3D printers, the materials that go into the machines, the software that drives the machine, and also the services that can be provided around that. So we take a very broad view of what is 3D printing. It's not just the machine itself. In fact, I would argue that that's not the interesting aspect. Because, really, where is the intellectual property in this ecosystem? Is it in the material that's being placed by the machine? Is it the machine that's placing the material? Or is it in the software that's telling the machine where to place the material? And truthfully, of the companies that we've invested in, they understand that it's all three. You can't separate one from the other. The material, the hardware, the software, it's all coming together in additive manufacturing, right? It's a trilogy that you can't separate. One of the companies that we recently announced that we invested in is a company called Voxelate that's out of the Wyss Institute at Harvard, led by Jennifer Lewis. So they had an invention in the laboratory around conductive ink, and they could print this ink that could carry a charge. So you can print a circuit inside of your 3D printed structure. So you can be embedded. So you can embed your LEDs, your motors. Now, things like the chip itself, they have to be manually placed, right? You can't print those yet. But the idea here is that you can have a blueprint that has all the materials in it. You push print, and it comes directly off of the print bed, all intact. Let's see if it plays through this time. So here we're using technology called 123D circuits, which is a circuits design application. So you can design the connection between your power source and your control board all in the 3D model. And it sends all of those instructions to this machine. So the orange is the polymer, the plastic, and that silver is the conductive ink itself. You place the materials in it as it's building, and again, when you're done, your drone can fly right off. So this is a company called Voxelate. They're in production now of these devices, and they're being distributed in a beta release. So this kind of stuff is happening. We're designing the actual materials. We're not just designing the shape of the thing, we're designing the stuff that goes into it. We're designing materials that never existed before. Think about that, right? In the history of the universe, we've been stuck with a periodic table of elements and the combinations of those things, and they all exhibit certain properties, such as this. Let's imagine that you're trying to design something that's very strong or very stiff and lightweight. In traditional materials, we have metals, which, if you look at, this is the weight, the density, and this is the Young's modulus or the stiffness. They're very stiff, but they also tend to weigh a lot. Titanium might be lighter than steel, but relatively speaking, it's still quite heavy. We developed a lot of new polymers, which are very stiff, but still weigh a lot. And then we have things like foams that we can create that help to bridge that gap. But what we've done is created a new breed of what we call computational materials, right? So this green area are materials that were designed computationally to perform like no other material has performed. Very lightweight, very strong, very stiff. And they're made up of these little microstructures. We're working with Lawrence Livermore National Laboratory. It's a research laboratory in the US. They call it architected materials because you're designing the architecture at the microscopic scale. And this is kind of what some of these materials look like here. So you can see this mesh structure, and these are made up of about 100 micron feature sizes, 100 microns. Really, really small structures. And what's interesting, one of the materials that they've made is a metal. It's very lightweight because it's this truss structure. And the metal shrinks when you heat it up. So think about that. Every metal in the history of the universe in 4 billion years, when you heat that up, it expands, right? That's what metals do. Well, this one does the opposite. And when you cool it down, it grows. Now, it's one small example of the kinds of things that we can do with computational materials. But the point is, again, we're designing the structure itself, not just the shape of the thing. Now, that opens up a whole another set of questions that traditional engineers don't like because they have a certain understanding of how things work. Metals behave in a certain way. They break in a certain way. So what happens when things don't behave the way that they naturally do? So these are some components that we're designing with this small lattice structure. And the challenge is that the structural engineers don't know how it's going to break. And if you're designing these to go on a car or an aircraft, it's kind of important for the human to have an understanding of the way things fail so they can avoid it, right? Well, this is interesting because we said, all right, we understand that concern. Why don't we prove to you that the software can predict how it will break? So we took all of these samples of these structures, these really intricate, complex structures, about that big, and we broke a bunch of them. And you can see that we're able to predict, if you see the little green spot there, that's that finite element analysis showing that that's the highest stress area. And the physical sample broke exactly where we predicted it would. So out of all these hundreds of little elements, we could predict which element would fail first, which is kind of interesting now. Our ability to predict behavior is getting real and in some ways surpassing the intuition of the human. Now this also opens up a vulnerability, right? Because now you think about, let's think about hacking, right? I don't know if you guys have read stories about now that people are able to hack the Internet of Things. So not only hacking into computer systems and stealing data, but they're actually manipulating physical reality. They're manipulating cars, for example. They recently hacked a Jeep Cherokee, and they could drive it from a laptop remotely. So imagine you're driving down the road, and suddenly somebody else is driving your car. That's pretty scary. But what about when people hack the actual material in the structures that are being made? What if somebody placed material malware in a very inconvenient spot so it wouldn't perform the way that you had predicted? You'd really have no way to know that this one little microscopic area had been changed. So instead of maybe printing that area with titanium, they printed it with cotton. Now, this isn't a reality yet, but I'm saying that this is something that we have to be aware of going forward, because traditionally, when you were just designing the shape of the thing, you had a blueprint, you had a drawing. And in order for somebody to copy that, usually you had to have a factory and workers and machines and a lot of capital in order to replicate that thing. But we're making manufacturing much easier. The cost of capital to make things is going down dramatically. Some people predict that it's going to cost 90% less to have a factory in 10 years than it is today. 90% less. Meaning you can have one machine that can make all these different products. It's something we call, the ease of compiling matter. So you think of computer programmers compile code to write an application. Well, what if you could just compile matter? You design the thing and you push print, and it puts all the right materials in the right place. That's the future we're going to. Now, another challenge here is the amount of data that we're going to be dealing with. It's huge. So let's ask Siri, how many voxels does it take to print an iPhone? Now, first, you probably want to know what a voxel is. You think of a pixel on a screen. A voxel is just a three-dimensional pixel. It's a little Lego brick. So imagine them as these little cubes of material, and you can have a little metal truss structure, you can have the conductive glass for the surface, so you have all these different materials to choose from that are these little cubes. And let's assume that these cubes are about 1 micron, 1,000th of a millimeter in size. And that's the resolution. Now, we're not there yet, but in 10 years, I think we'll be there. We'll be able to print at this resolution. So how many of these little cubes does it take to make an iPhone? Any guesses? Order of magnitude? Millions? Billions? Almost 90 trillion. 90 trillion of these little things to make that. So what does that mean in terms of data? If each one of these little things is about 50 kilobytes, which is a pretty conservative estimate, it takes about 3.5 petabytes to represent something the size of a phone in your pocket. 3.5 petabytes, right? Gigabyte, terabyte, petabyte. It would take a couple of weeks at a 1 gigabit per second connection to stream all the data for this phone. Now, we can compress this, and there's a lot of ways to optimize this. So this is a worst-case scenario, but my point is that the data size of the designs that we're going to be dealing with will be enormous as this technology advances. So let's talk about this idea of compiling matter. What happens when we can quickly and easily take all these different materials and put them together? Does anyone recognize this little block that I just put up here? This little voxel? Right, so we have our little metal one, we have our little glass one, we have our aluminum one. What's this one? I see a few heads nodding out there. Any gamers? How about this? Does that recognize? Yeah. Minecraft, man. We already got it. We've already got this tool where we can take all these different materials with different properties and compile them. What you're seeing here is a functioning CPU, a computer that was built inside of Minecraft. Think about that. A bunch of people got together, because this is very collaborative, right? You can see everyone else running around. I play this with my nephews and nieces all the time. You see the little people running around dropping little blocks of material. And the little blocks of material can be conductive, they can be structural, they can be bouncy or squishy, they can be clear, they can be opaque. And people have made functioning 3D printers inside of Minecraft, made functioning hard drives that can store memory inside of Minecraft. It's very postmodern, very meta. But now think about it. What happens when they have a compile button? So you've designed a functioning computer in the shape of a chair inside of Minecraft, and you have a button that says print. Probably wouldn't go that fast, by the way. It may take a couple of days. But imagine what happens when we can print that. How does our entire world of design change? Our designers themselves will change. There's hundreds of millions of people playing this game. Most of them are this size or smaller. And they're good at it. They're a lot better. My nephews and nieces are much better at this than I am, and I'm like a professionally trained architect. It takes me forever to do anything in there. So this is our future matter compiler expert. His name is Steve. And fortunately for us, the people controlling Steve are pretty awesome. They're not scared. They're not afraid of failure. Right? Kids run in and they love breaking stuff. It's like they almost want to break stuff. We have a booth. We go to Maker Faire every year, which is a big event in the U.S. around making, things like 3D printing and crafts. And we have a big booth showing some of our consumer technology, which is accessible. It's free to everybody. So we have 3D design software, and we have something called 123D Sculpt. And it's basically a digital sculpting environment. It's like digital clay. So there's a little iPad set up in the booth, and you start with this little ball of virtual clay, and you can start sculpting it. And it's funny because at Maker Faire, it's a lot of like nerdy parents, like engineers and designer parents with their kids, and they come up, and the kids just run to the iPad, right? They're like going crazy and making stuff and printing it. The parents are like touching it like that, like they're afraid of it. Because they're afraid they're going to break the technology. We grew up in a generation where if you push the wrong button, things would explode. And then somebody would be really mad at you. But now this stuff is so cheap and so accessible. Now you're uninhibited by technology. You're empowered by technology. And they get it. They're using it. They're using advanced machines. Now, this is part of the reason that at Autodesk we built this research facility called Pier 9, which is a mega fab lab, if you will. Basically, any machine you can imagine, big routers to cut metal, water jet cutters, 3D printers, welders, robots, it's all there. It's like a fantasy land, honestly. And this is so that our engineers and our partners can experiment with going from a design all the way to the physical thing. Because we realize that people don't usually design something without the intent to make something. So how do you connect the design to the making? Now, we've also opened up a very interesting program called the Artists in Residence, where people can apply from any background: fashion, architecture, product design, fine art. We even have writers and authors that come in and apply and get a residency, so they get to hang out in this space and make whatever the hell they want to. So is that video going to work? We do have a video if it'll play, if the broadband is fast enough. But I wanted to show you guys just to give you a flavor of what this thing is about.
It's a sort of freedom, a freedom that you have when the city is asleep. It's really cool to jump in here whenever you have inspiration, this impulse that you need to do something, even if that's 12 o'clock or 2 o'clock or 4 o'clock at night. We want to produce because it's about feelings that you have, or it's about statements that you want to make. I have one purpose, to move something in people.
Working on the pier in the residency program is this incredibly unique opportunity. Everything on the pier is about exercising your kind of innate human ability to shape the world around you, to reflect something in your mind. I've never seen such a kind of a density of diverse interests and talents all in one space, just with the sole directive being to exercise that talent and kind of to cross-pollinate, to have discussions that would never kind of happen in the wild.
The Artist in Residence program at Pier 9 is a thriving community of people from diverse backgrounds who are united by a passion for sharing what they make. Our goal is to create the space and environment where artists are encouraged to challenge themselves to create work that the world has never seen.
You have a different way of exploring the tools and the software here at Pier 9. Those artists go out there and ask the tools and the people to do things that are just crazy because they're right at the edge. They're like, why can't I do this?
Então, o programa aqui é muito livre, assim, né? A gente tem uma liberdade muito grande, não só conceitual, do tipo de projeto que a gente vai fazer, e a gente tem muita liberdade para aprender, para errar, para experimentar.
I've had several instances where I can just design a part in the morning and then hold that very part in my hands later that afternoon.
What makes this Artist in Residence program unique is not just the workshop that we have available to each artist, it's the supportive community that we've developed, not just within the Artist in Residence program, but beyond that with Instructables and Autodesk. By being able to be hands-on on all the equipment, they really get to understand what the tools can do and create really amazing things.
In the past, I've mostly created things with my hands. I have a fashion background. And the main new thing I ended up exploring here at Pier 9 was 3D modeling, which is not something I'd used extensively. And through this one project, I ended up learning a lot about 3D modeling and getting to explore this really interesting form. And through that, starting to see how all this new technology could have applications to my own creative process.
You might come into the program with some specific ideas, but chances are through the collaborations with other artists here, your ideas will change in unexpected ways, and you have the freedom to morph your projects into anything.
I think the point for me and the other artists here is to make things that we're obsessed about.
Failure is really how we move forward. And by failing at something, you'll find a new and unique way to do it maybe the next time around. You can really push the boundaries of what you're comfortable doing, and the creativity and the wealth of knowledge here does really enable you to make anything you can dream of.
Cool, huh? So who is going to apply to be an artist in residence now? You should, by the way. It's an open application process, so go be part of the magic that happens there. That's actually where I work every day, so I sometimes pinch myself to realize that I get to work in a playground like that. It's cool. But here's the thing, is that it doesn't just take a space like that to be creative and to make and to invent. Does anyone recognize these? 2011 floods, right here. And look at what people were able to come up with as solutions. They didn't have anything. They didn't have 3D models or 3D printers or laser cutters. They just had the materials around them. A raft made out of bottles, brilliant. Stilts made out of stools. That's a pretty cool idea. Now, what happens when you give these people the tools, right? I'm saying there's this latent, this amazing creative potential here. And if you empower people with those tools, imagine what they could do next, right? And I think that's what TCDC is about, and I think that's where you're going, is I hear that you're going and creating new maker spaces, enabling more people to have access, because this isn't just about a small group of designers, this is about the entire community. There's no reason that everybody can't be a designer or maker. With that, I thank you very much, and I guess we'll open up to questions.
So I really like the way you framed this about being about failure, and especially in the sections when you talked about the ability to iterate almost endlessly with machine-assisted design. When do you know you've failed enough? Like, any rules of thumb, or is it totally contextual based on the problem you're trying to solve? When do you know I've got 1,000 iterations of a design that this is the one?
That's, I think, the question, actually. So great question. And the question is, how do you know when you've attained the solution? I mean, the non-imaginative answer is you run out of compute time and the best one you end up with is the right one. I think that this is where the human interaction plays a very critical role, because there is an intuition that I don't think we're going to mimic with machines anytime soon, in any predictable future, of when a human can see that, look, I have met the requirements. I'm as lightweight and as strong and as energy efficient as possible, but some designs have a much more compelling emotion, right? Aesthetic is not one of the criteria that we're optimizing for. Aesthetic is not something we've codified. And I think that the human interaction, this is the important part. And the challenge will be when you're inundated with so many options that you kind of lose track of what you're going after, right? And this is an ongoing challenge. The user interface and the experience of that is still, I think, one of the hardest things to do, in addition to all the computation and the engineering that happens. And this is where good designers will still shine. I still think that, this will enable anybody to at least come up with something that solves the problem, which is exciting. That democratizes access to designing and making things. But there will still be the designers who have this ineffable quality that none of us others can attain, and we'll see some of those presenting over the next couple of days. So it still retains that sensibility that we can't quantify yet. And at some point, you're just going to say, stop, I've seen enough, this one's good enough, let's go with it.
In the near future, do you think the relationship between human and machine will shift from user, tool, medium to worker, co-worker?
Yes, I do. I think we're going to see machines as our collaborative counterpart. We're not going to just see them as an output device or an input device or a processor. They will become our collaborators. And there will be some empathy there. I mean, we've already proven that children, when they're talking to a robot, are more honest and are more willing. Even adults, actually, they're starting to do these tests where we feel more comfortable in telling the truth to a machine than we do a human, because we don't think the machine will judge us. Now, I'm not going to determine what the psychological outcome of that will be, but the point is that humans are willing to collaborate with machines. We are willing to see them as peers, not just as, our workers.
The development of high technology will enable handwork done by machine in a perfect quality. What will be craftsmanship meant in the future? Will the future artifact lose of human touch?
I think there's two answers here. One, there's something, and this has been talked about in digital architectural circles for over a decade now, about digital craftsmanship. And there's good ways to design something digitally, and there's bad ways to design things digitally, just like if you're doing it by hand. And it's evident in the outcome if somebody used a good process or a bad process. And there's also artifacts through these digital processes. When you're machining something, you get the tool path. You can actually see the cutter head. And some people have learned how to exploit that. In fact, one project that my advisor, when I was doing my PhD at school at Harvard, he was working with water jet cutting marble. So you think about marble as a natural stone, and it has veins and varying density, right? So it's kind of an amorphous material in the sense that it has a lot of variability throughout the structure. And then he had a robot with a water jet cutter on it. So a very precision-controlled robot that would cut and carve the marble. What was interesting is that as the water interacted with the marble, it would start making swirling patterns because it hit a dense area and then it hit a soft area, and it ended up coming up with this really beautiful texture that wouldn't have been able to do by hand. A human can't hold a water jet cutter in place. And it was beautiful because it had the precision of a robotic cutting, but then this crazy random texture that was driven by the variability of the material. So that was a digital artifact, which I thought was very cool. Now, the other side of this is that I think in Etsy, this online craft marketplace, I think is evidence that we're going to have renewed zest for handcrafted things, things that we know was made by a human in a totally analog way. And I think the market for that will continue to go. So most mass production will go to automated design. And that's good, right? Because it consumes less resources. For all the chairs in here, we're not really that concerned about the design of these chairs from an aesthetic point of view. We want them to be comfortable, we want them to be efficient to manufacture, cheap to purchase, and consume less materials. So for things like that, I think it's great to automate design. But for your jewelry, maybe you want something that's handcrafted. So I see both of these evolving, actually.